Today I want to talk about the mapping, that is the relationship between your code and its performance on microcontrollers. So despite its title, this is not a talk about C++ only. This is really for all embedded programmers. Any idea what this is? What this might be? A map, okay. In fact, it's a pretty old map. It's a world map from around 1459. And you see Europe here. This is Africa. And you see, for this time, there is a lot of detail in the map. And unfortunately, this detail is misleading. Take a look here at Southern Africa. I guess this should be Madagascar here. But if you compare this to a modern map, it's totally off. It's just wrong. And it's historically shown that the creator of this map, who lived in Rome, did not know about it. He'd never been there, he didn't read about it, he just made it up. Another map. This one was created about 60 years later, and it's totally different. You see a lot of empty space, and you see a new continent. So in the meantime, Columbus discovered America. And people learned there is something we didn't know yet. And it's really interesting because the level of detail is less. And you see that the coastline is pictured here, this new continent. There are some trees indicating there follows something, but they didn't know what. So they left it empty, intentionally empty. So in the meantime, the mindset shifted dramatically. The people admitted they don't know. And this had major consequences. It marked the beginning of modern science. Modern science is characterized through two main ingredients. Firstly, admit ignorance. Admit that you don't know everything. Second, observations. Measure and gather data and use this data to create some theories or maybe draw a map, but data-driven. Another impact. This graph is showing the wealth, the world GDP, over the last 2,000 years. And as you see, this is mostly flat, which means, imagine a guy living in the year 1000, falling asleep, taking a deep, deep nap, and waking up 500 years later in 1500. Okay, all the people he ever knew are dead, long dead. But despite of this, not so much changed. The technology was the same. The people behaved the same. And now, another nap. He's waking up in the 2000s somewhere in New York. He would not recognize anything. All changed. And one influence was this modern science thinking. Yeah? Create theories. These theories eventually led to, for instance, Newton's laws of motion. These laws were used to create machines, which brought us the Industrial Revolution and which brought us onto this vertical slope of growth. Okay, so this change in mindset had major influences. The connection to embedded. I think regarding our understanding of code and its performance, we are somewhere here. We don't admit that we don't know. What do I mean with this mapping? Imagine you have your code, compile it, bring it on some microcontroller and measure its performance, its runtime. How long does it execute? How many cycles it's using? There is some relationship in between. Something has to determine how the performance will be. Several factors come to mind. For instance, the target architecture. Yeah? Are you running on 8-bit, 32-bit, an ARM, whatever? Do you have a cache? On what clock speed are you running? What compiler are you using? An old one, a new one, which version? What settings are you using? Yeah? Are you using a debug build or just an optimized build? So all these factors are highly complex and possibly they depend on each other. And I believe that we as embedded developers, we are largely ignorant. We don't understand this fully, yet we don't admit it. And talking to other developers in the embedded domain, I sometimes feel like this. There's a lot of belief in our domain, but not a lot of data to back these beliefs up. So this has major consequences. Firstly, prejudices prevail. Like we heard today already, C++ is too slow for my embedded system. Something like this. You really hear it all the time. We have a mistrust against libraries. I think Dan Sachs called this mistrust against abstractions this morning. It's basically the same. People reinvent the wheel all the time. Yeah? We don't rely on experts who are writing libraries. No, we better write it again and again and making mistakes in the process. And this is leading to low code quality. You see this everywhere. If you want a few impressions, go to Twitter, check out Kevin Henne's feed. He's collecting pictures of embedded systems which crashed in the wild. And this is bad. This is really bad. Performance suffers. Obviously, if we don't care or if we don't know about this mapping, performance will suffer, which means we have to use faster hardware, which is costlier, costs increase, battery time decreases because the energy consumption is rising. So a lot of consequences. So let's first admit our ignorance. Let's admit that we don't know everything. And then let's use observations. Let's measure. How is this currently done in embedded? You have two things to consider. The one thing is profiling. This is a top-down process, so you have your program, you compile it, bring it on your target, run it. And then you attach some usually pretty expensive tracing hardware, and you observe, you generate statistics where the program is spending most of its time. So this is great to identify bottlenecks, but pretty bad to understand to create a specific understanding. I think it's better to build knowledge bottom up. So take a piece of code, measure it, observe its performance on your platform, and then create heuristics. Heuristic is something, a little theory, a rule of thumb, something you can communicate easily. How can we do this? I will proceed with using the ARM v7m architecture. So this is pretty widely used architecture. Cortex M3 and M4 are both running on it. So we will only view bare metal systems here. This architecture is great because it's providing a so-called data watchpoint and trace unit. This little unit, it's a little bit of periphery inside your controller. It's providing performance counters. And one counter being this cycle count register. So this register is telling you how many cycles your controller spent executing your program. This is really great because it's the most detailed result you can get on an embedded system. So how can we use this? Let's use it to measure our cycles from a piece of code. Assuming we have a little Cortex M4 processor here, which contains this unit, we attach an off-the-shelf JTAG probe to it, and then we use some free OpenOCD software to connect to use the JTAG connection. So this is pretty cheap. The controller starts at a few euros, and the JTAG probe, you get it from China for a few euros. So nothing compared to the thousands of euros for tracing hardware. How do we measure the code? We just use this breakpoint instruction. This is an ARM assembly instruction, which basically stops the execution and holds the core. So you stop it, then you use your JTAG connection to read the current cycle count register. Then you proceed to execute the code you want to test. Maybe a statement, maybe a function, maybe a bunch of functions. It doesn't matter here. Then you stop with the breakpoint again, read the cycle count, and you can say exactly how many cycles were taken. Great. Let's use this to make observations. First example, basic optimization. Imagine you have a function which just squares its input. How fast is it on an embedded target? Let's measure. If we use a minimal optimized build, this is -OG on GCC, it's executing in 6 cycles. 6 cycles because you need to branch into it and then execute it. Unfortunately, if you use no optimization, which is the default on GCC, it's executing in 4 times as much cycles. So there's a difference. Where is it coming from? Just look into the assembly. The minimal optimized version is just straight a multiplication and the branch back. The non-optimized version does a lot more. It doesn't make any assumptions about the function. So, for example, it needs to save the input registers onto the stack. It's pulling them back, calculating, and then returning. So a lot of boilerplate here for this function. This leads us to heuristic number 1, rule of thumb number 1. The difference between minimal and no optimization is huge. And this is important because from experience, I know a lot of programmers, embedded programmers, are just running without optimization. Maybe they don't know about it, about this heuristic. Maybe their toolchain is so crappy that they cannot debug optimized builds or something. This is a real problem. And it leads to major, to wrong assumptions about some code and some libraries. Next example, our pipeline. This processor we have, it has a 3-stage pipeline. And let's see what influence this might have. Assuming we have a function which is doing 2 divisions and then returning the sum. In case we compile this with O1, this is optimizations enabled, GCC replaces firstly this division, which is slow in hardware, through a multiplication using some fancy magic key it calculated, a magic value it calculated. So 2 divisions and then return the sum. Okay, straightforward. In case you enable even more optimization, you get a different result. This is in fact the same statements but reordered. Why is it doing this? Let's run this function one time and see how many cycles are spent. You see that the more optimized version takes 1 cycle less. I think this is due to the fact that at this stage here, it's loading this magic value, this one here, and in the next instruction, it's multiplicating this value with something else. Usually, this will incur a pipeline stall. The compiler knows about this, and in the really optimized build, it's loading both magic values in the beginning already. This leads us to heuristic number 2. In low-level assembly, the compiler is probably way smarter than you, so trust it. Third example, and the last one where you will see any assembly. Floating point. Imagine we have a function multiplying its input with pi displayed in floating point. How fast is this? In case we compile for a target which has a floating point unit, little hardware unit which can do these calculations, the compiler just uses these assembly instructions. Okay. In case we don't have this, this is looking different. The compiler has to soft emulate it, which means it provides functions for this. They are shipped with the compiler usually. And it's using these functions to calculate the result, yielding the same result as the hardware, but through software. And how to reason about the performance of this? It's very difficult. Up until now, you can basically, if you have a lot of time, just take up the reference manual, look up how many cycles each instruction needs, and calculate and sum it up. This will be roughly right, roughly because it doesn't take into account pipeline and cache and things like this, but you have an estimate. Here, with branching, so branching, loops, everything involved, you cannot make an easy guess. You really need to execute it, at least in day-to-day work. Maybe not in academia, but in day-to-day work, you need to execute it. Doing this with a range of input values yields this result. For the floating point unit hardware, we have constant runtime. For the emulation, we don't have constant runtime. So it's depending on its input, how many cycles are spent. You can be easily misled when you just check out one example. Heuristic number 3. For our architecture, for our processor, for our compiler version, the software FPU is around 6 times slower and not deterministic. Okay, last example, CRC calculation. CRC is a mechanism to calculate a checksum on a range of data. It's done to detect corruption in this data. And there are 3 options I'm aware of to do this. Either by direct computation, just straightforward implement the algorithm, by using a lookup table, which is some table with pre-calculated values, which can later be used to speed up the calculation process, or by using hardware support, in case it's available. I want to check here how these factors I mentioned, how the target architecture, how the target speed is affecting the performance of this code. For this, I will use a platform called barebench.com. This is a service my company created because we really didn't found anything to do this easily. It's in a very, very early technical preview stage, and it's allowing you to execute your code on real hardware. So web front-end to execute this. In case you're interested, there's an email address on the website. Just write us, and we will provide you access for testing. Okay, so let's start with the demo. This is too fast. Okay. Please don't focus too much now onto the specifics of the code or something. I really want to show the process, how it's working. On the top side, we have our 3 algorithms. So the first one is a direct computation. So it's just some loop and some calculations. The second version firstly defines this huge table, and then uses this table to do the calculation. The third version is just using special function registers to use the hardware. And all these functions have the same signature and the same name, CRC32, and they take an int to determine how much data they should take into account. They are all relying on this global pointer to some data to execute. In the lower side, we do the benchmark, the actual starting point. We define a function. We define which function we want to benchmark. We define some sample data. This is just random data to do the checksum calculation on. Set the pointer and then call our function with different lengths. Okay. Now we need to define on what target we want to run. Let's assume we have this. We want to run it on this STM32F4 Cortex-M4 processor, and let's benchmark the direct version against the table version. For all examples, I will use full optimization because otherwise the results cannot be compared. So now this is compiled, loaded onto some actual hardware, executed there, so there's no emulation involved, and we have the results. Okay, so you see that the direct approach here is taking way longer. Okay, the table approach is about 8 times faster if you look at the difference. Okay, this is expected. That's why you use the table in the first place. It should be faster. So keep in mind this is 8 times faster, and the execution time for the direct one is in the worst case 8,000 cycles. Let's run this again now, but using another clock speed. So this fast configuration here will use the same target, but configure the PLL so that it is running on maximum frequency, which is, I think, 168 megahertz for this processor. In the normal configuration, it was running on 60 megahertz. So let's see if this change is changing the results. Keep in mind, we are comparing cycles here, not execution time, but cycles. And we see that it got worse. The direct approach here is taking now almost 23,000 cycles, and the table approach also a lot more. The difference is still about a factor of 8. Okay, this might be due to the fact that we didn't enable caching. This processor has a data instruction cache, which we will enable now and try again. And happily we see the results are back, at least for the direct approach, back to the starting point of 8000. Unfortunately, the table approach is right now only 4 times faster. So there seems to be a dependency from the algorithm to the cache settings and the frequency. Let's try to isolate this and just run the same version against different frequencies. So we will use the F4 with cache enabled, the fast clock speed, and the fast clock speed with cache enabled. And of course everything, so the compiler stays the same, the optimizer stays the same. Let's run this. And I will switch the display because they are overlapping here, the results. You see that 3 of these configurations are yielding approximately the same results. Only one is outstanding, and this is fast clock speed without cache enabled. So we can infer from this that our flash is just slow comparing to the clock frequency. So each data load induces a stall, basically, wait for the flash. And this makes our algorithm slower. But the good news, if we enable caching, it stays the same, which means our algorithm is somehow scaling with the clock speed. In case we double the clock speed, the runtime is cut in half. And this is great to know because it's a good property to have. So let's skip this cache not enabled for high frequencies, and let's compare the table-based approach. Okay. So the table-based option is taking longer for higher frequencies, higher clock speeds, despite the cache being enabled. This means this algorithm is somehow not scaling with our clock speed. This is rather bad. Okay. Last example, because I mentioned it, let's check the hardware option, because our controller here has the option to calculate checksums directly in hardware. Okay. As we would expect, the hardware, you barely see it here. This is a purple version, purple color, is taking not the less cycles. You can compare here the actual output to see that all 3 options really yield the same result, which is, by the way, for CRC pretty difficult. I needed several hours to get the hardware deliver the right result. Okay, so back to our presentation. What did we learn? Firstly, performance may be dependent on clock speed for this target. Second, caching is essential for high clock speeds. We really need to enable this. The flash is too slow, otherwise it will screw up everything. Conclusion, summary of this talk. Please admit a lack of knowledge. Let's all admit that we don't fully understand this mapping, because it's too complicated to fully understand. Let's measure the performance. Let's use the data we obtain to form some kind of theories, heuristics. Discuss them, share them with your coworkers, publish them, write me about it. And please use these heuristics instead of prejudices. If you want to reason about a library, if you want to argue that you can use this library, back it up with data instead of just believing. So let's use this to make embedded systems better. Thanks for listening. Any questions?
On the last slide where you had assembler, I was wondering on the right side why register 3 was saved.
Sorry? On the last
slide where there was assembler on it.
Yeah.
No, slide, not.
Slide, okay. Which one?
With assembler on it. Back. Yeah.
This one?
Yeah. And on the green one, why is register 3 pushed and popped?
A tough one. I'm not sure. Maybe GCC is using L3 as a frame pointer here for debugging purposes, but I'm not sure.
Okay, maybe it disappears with higher optimization. You were using O2, I think, not O3. Because it
this should be on O2, yes.
Yeah, it doesn't seem to be doing anything. Okay, thanks.
Other questions? Keeping with the theme of crazy assembler questions, can you speak to how you're actually implementing the benchmark?
Yeah, so you always have the problem that you fight against the optimizer there. I tried several approaches, for example, using the mechanisms in Google Benchmark. This is all pretty complicated and compiler dependent. And I ended up with just using a different translation unit. So link time optimization is not enabled. And this pretty much is okay for most measurements. So I'm optimizing here only the different translation unit.
Okay, yeah.
Other questions? Well, thank you for the talk.
Thanks.